Mhm.
Awesome. Right. Good afternoon. Time zones are always confusing for me, so who knows whether it's afternoon or evening yet. But hello, thanks for having me. Anyway, I'm Jamie. I'm a PhD student at Imperial College London, and for the last who knows how many long years, I've been working on Parser Combinators, and my goal has been to make them fast and to make them more mainstream. And I'll touch a bit on how far I've got with that goal today as we go through. So before I start, I think I've sort of split this talk in two. So the first half has slides and sort of outlines my work so far, and how roughly it works and what parser combinators even are. The second half is a bit more open-ended, so I'll just go in directions that people want me to go. I have various things I can do, and so yeah, I can just do that on the fly. But we'll make a start with what I've got so far. So the outline for this sort of half is I'm just going to outline, what parser combinators are and what's the difference between monadic and selective parsers, because for my work, there's like a pretty important distinction between the two. And I'll talk a bit about optimization and what analysis I can do on what are called deep embedded parsers, and I'll explain what that is, and how I compile that to a stack machine, which is what I run with. And I'll elaborate a bit about staging. I won't go into too much detail about it. It is something I can go into more detail about later. Essentially, how do we actually go from these representations of parsers to efficient things? I know this will all become clear as we go through. I just want to sort of give a brief overview of what we're going to end up doing. So I'm going to start with describing parser combinators, because perhaps not everyone's aware of what they are. So in the world I'm sort of thinking of, parser combinators have a few sort of key operations. I think the most important one is this satisfy operation. So what that means is if you give me this function from characters to bools, and that basically says, say, the function returns true on A's, then this function is looking to read A's, right? And if it returns true on A's and B's, it can read either an A or a B, right? So if the function returns true on a character that's next in the input stream, then this parser will return that character and eat it from the input stream. So a sort of very basic building block you can build off of this is like the item combinator that basically just says, anything goes. So just read me any single character from the input stream if it exists. If it doesn't, the parser will fail. There's a few others that are sort of very specific to parsers. So you've got try or cut. It depends on what library, what implementation, what style. They're basically opposites of each other. And try essentially is the one I'll be working with, and it says that you can backtrack out of a certain branch. So by default, you can't backtrack out of something. With try, it allows you to sort of rewind input consumed to try a different branch. Look ahead and not followed by are also in some sense opposites. So look ahead will pass something, but won't actually consume any input in the process. So it's sort of verifying, can I find something? And it returns some result A. If that passed correctly, I'll give you back the A. Fine. Not followed by is similar, but it says, can I not read something? So, whatever I pass, it better not be the thing that's in this first argument. And so it can give you no results back. So it just gives you a sort of nice intuitive way of putting some of these things together is that we can work out if we've reached the end of the input by asking if there are no more items. Right? So if it's impossible to read anything at all, then we must have reached the end. Great. So those are sort of like these primitives, and they're not really very useful. I mean, we could read at most one character with this model. So the whole idea is we build up on these things called combinators. Now, for the sort of Haskell side of this, and for some extent the Scala story and other languages that are quite functional and are quite built on this model, there's a hierarchy that goes from functors up to monads. So we have functors. they allow us to map results. So if we have an FA, we can use a function to turn it into an FB. Applicatives, sort of similar thing, but they allow you to extract the function from another common structure. So, you're taking your functions returned by one parser and applying them to results of another parser, and you can get another value. And alternatives give us an ability to either fail or do some alternative actions. So either we try this thing or this thing, and we'll take whichever result succeeded, if any. So the sort of idea for Parser Combinators is you're building on these to start doing more and more complex behavior. So we can actually use regular Haskell or Scala or Camel functions to build parsers with these combinators. So here are a few of my favorite examples, just to give a sense of what that means, because it's not all about generating, writing out grammars specifically, but also how can we make tools to help write those. So sequence and traverse are very classic Haskell functions. The sort of type tells you a bit about what they do. So sequence says, if I have a list of actions that I need to perform, I can sort of do them one after another and put their results into a list instead. And traverse is very similar, except we take a bunch of values and we can transform them into actions with some function. So I'm not sort of going to dwell on how these are implemented, but the critical insight that I want to get out of this is we can build this combinator called char, and that's built on top of the satisfy primitive that I showed before. So we can read any specific character with this. So if I pass it A, I'm asking, is the next character equal to A, right? And the magic thing for me is that if we give a list of characters, we can traverse over that list with this character combinator, and we immediately learn how to recognize strings. So we have a list of characters to pass with a list of characters, which in this case is a string. And that's perhaps one of my favorite combinators because of just how beautifully elegant that it ends up being. As another example, one of basically says, can I read any of these characters that you give me? And this can be done by turning each of these characters into a parser that recognizes a specific character, and then folding them all together using this OR operation. And if there are no characters you want to read, it just fails. So, if I say one of the empty list, I can't read anything out of the empty list. So this parser obviously just fails. So these are sort of a few examples of sort of abstract examples of how you can start to build up more complex toolbox out of these more primitive operations and these applicative and alternative combinators. But I'm going to show some examples now of some actual practical parsers. So just to sort of outline how parsers end up looking with respect to some grammar. So for instance, I can build a parser that reads non-zero digits, and that is one of the digits 1 to 9. If I wanted to make a digit, then I need to add 0 to this. So I can say something like, is it the character 0, or is it a non-zero digit? So any of 1 through 9. And then if I want to start making natural numbers, I can say, well, first read a non-zero digit. So we're choosing here not to allow 0 as the first character, and add that onto the front of the result of reading many digits. So many and some are basically regular expressions, stars and pluses. So this is the cleaning star operation. Cleaning plus is called sum. So this reads 0 or more digits, adds on a non-zero digit onto the front, and then we're going to use fmap here, which is written in combinator style as a dollar, and just read it. This is kind of cheating, but to fit it on a slide, I'm not going to go with the version that actually turns a list of digits into an integer. So read will do for me here. But read is turning the list of characters returned by this parser into an integer. Another example here, identifiers. So we can ask for anything that satisfies the function is alpha. So it's an A to Z. I think maybe it might even map some characters from other character sets. I'm not entirely sure. And we can add that onto the front of 0 or more, again, alphanumeric characters. So we're also allowing for 0 through 9 in this case. So that's basically how these things sort of build up. And I won't give any more complex examples until the second half. But just sort of give you a sense, these are the sort of building blocks and how things start to piece together. So, to convert a grammar, roughly speaking, you're using, this OR operation to represent alternatives in a BNF. And these sort of other ones are being used. This one's kind of doesn't exist in a BNF grammar, but these are being used as like sequencing, which really is just sort of a space in a BNF. So the real challenge with Parser Combinators is just knowing which operators to use to combine things, and that can be something that I touch on in the second half, depending on what people want to see. So my sort of next port of call here is to discuss, well, where do Parser Combinators fit on the spectrum of parsers? And I've roughly grouped them into three blobs. So we've got parser generators. That's stuff like Antler or Happy or I think OCaml Yak. There's a few of them, Bison for C, things like that. They normally take in BNFs. And so what I've said here is actually really the strength of these generators is how similar they are to the grammar. You literally write out grammars and parsers will pop out. The other class is hand-rolled parsers. So these are ones which you write by hand, your classic recursive descent or what have you. These are awful in terms of looking like grammars because they don't at all. But what they're really good at is performance and to an extent error messages because you get a lot more fine-grained control. Parser Combinators sort of sit in the middle. So they're written in a language which makes them more similar to hand-rolled parsers. They are recursive descent, which is similar to hand-rolled, but they sort of use these combinators to mimic grammars in a certain way. So it's a bit more structured and it helps make that translation a bit clearer. So they're sort of okay at everything, realistically. But in general are sort of okay at most things. They're not really amazing at anything in particular. So if this is the sort of current state of Parser Combinators, here's where I want to get to in the future. So I really want to work on their performance and get them to be great. I want to work on their error messages and get them to be great. I can't really make them any closer to the grammar. They are. And I want to make it quite easy to debug them. A lot of languages, a lot of libraries these days don't really have great debugging capability. It can be quite tricky to figure out why they're going wrong. And the analysis potential of these things, I want to make a lot better so that, the libraries can do transformations and optimizations similar to how parser generators can. So my work sort of exists in a form called Parsley. And here Parsley is at the moment. So at the moment, I've achieved the great performance, right? And I'm not going to quantify it today, but, to give a sort of rough idea, I'm usually faster than the parser generator library for Haskell called Happy. I can come within about 30% of the speed of C's parser generator library. So actually, it's sort of getting close to hand-rolled performance. There are improvements that can be made. There are challenges with making it even faster than it is, but the performance is already really good. Error messages, regrettably, still aren't done. At this point, I roughly know how to do them. I just haven't built all the infrastructure yet to allow me to make that jump. And debugging experience isn't so bad. There's debugging combinators to help with that. It could get better still. And analysis, it's already doing pretty well for itself, but there's a lot more ground I can cover. So in order to sort of explain really what Parsley's about, I kind of need to cover monads and specifically why I can't use them. So something key about this is Parsley describes itself as a selective parser combinator library. There are no monads. And I just sort of want to briefly touch on that point a bit. So here's monad, and it's basically an applicative with this extra bind operation tacked on. So it basically allows you to run one action and use its result to build another action that you go and then perform and return the result of. So what's the problem with this? Well, if I give you some examples first, and then I can sort of try and illustrate why is this not okay for me. So for instance, I can actually turn Parser Combinators around on their head and actually say that item is a primitive and satisfy can be built out of it, so long as I have this bind operation. So the way this works is read any character at all, call it C, and then if f of C is true, then just return C again, otherwise fail, right? So this sort of realizes the behavior of satisfy in terms of item instead of the other way around. And something I can do is I can extend identifiers now. So it still says, read an alphabetical character on the front of alphanumerics, but take it, we'll call it V, and just so long as it's not a keyword, return V, otherwise fail. So this sort of rules out, the idea that you could pass if and call it an identifier. That's not normally something you'd want to do unless you have soft keywords or something like that. So bind is super useful for stuff like this. And so you might, wonder, well, why is it bad? I mean, these examples are sort of giving this idea. It's sort of filtration. So, you have something, you can make sure that it adheres to some condition and carry on. And filtering, we've just seen, is really useful, right? These are the sort of more concise versions to make that clear. What's the problem? Why can't we deal with this? And what on earth are selectives? What's that all about? Well, the problem is with my last point from the outline. So I said I want to eliminate this performance overhead using something called staging at compile time. Now, compile time is the key word here. So that's the problem, right? And, why is it a problem? Well, if you look at this little diagram box, we have some parser P, and we're doing bind, and we've got something that we don't really understand on the right-hand side of it. The only way we can know what happens next is when we get the X out from P. So once we've seen X, we can use that to make this new thing Q, and then we can go on and do what happens next. The problem is that this X appears at runtime. So we don't know X until we know what the input is, and we've actually run through part of the parser. And so, well, we can compile P. We know what the shape of P is. We know all of its structure, but we have no clue what's on the right-hand side of this bind. Simply put, you just can't compile it, right? We don't know what it is until later. So, selective functors then. What are they? Selective functors, they were introduced a couple of years ago. I think it was ISFB 2018. And they have these two operations. I sort of prefer to talk about branch. Select is the one that they present originally. So the idea of branch is basically, if you have an action that returns either an A or a B, then given something that can turn A's into C's or B's into C's, you can get a C. And the idea is, if you got an A out of the first thing, you're only going to use this first option. Otherwise, you would only use the second option. So you don't do both. You do one or the other. And that's where the extra power comes from. So let's have a look at these types. And I can sort of explain where the difference lies. So with bind, we can make choices, right? We can decide what to do. We can decide what MB to do based on A. That's fine. But the problem is that, we can't find all of the possible MBs ahead of time. With branch, we know what they are. So there's either this first one or it's the second one, right? We know their structures ahead of time. We just don't know which one's going to be picked, right? So we don't know what the either is at compile time, but we do know what the outcomes are. So to sort of make that a bit clearer, if you look at the definition of filter for the Monad version, we can see that the orange code, which is colored in here, is found inside this sort of light gray box. And inside the gray box is a function, and that's something that we can't inspect. So it's like non-compilable. So we can't make any progress because there's orange stuff inside the box. The selective version, and I'm not going to explain how it works, the key thing to sort of see here is there's nothing inside the box that's orange. So all the color is outside of these boxes. So that's really important. That means that we don't really know how this function behaves at compile time but the key is we don't need to, right? We know what the outcomes can be. We can figure it out later. So it turns out that this filtering operation that we saw being so usefully used earlier is actually selective. So it just about works on its own. So we don't need bind for this stuff. And sort of natural question is then, what can bind do that select can't? And the answer is they can't implement join. So they can't take a parser that returns a parser and sort of collapse it into one long action. And they can't keep results alive for longer than, instantaneous use, unless you keep, throwing around co-products, which can get really messy really, really, really quickly. As it happens, for most use cases, I don't think these two things are important. But, is there a way we can get that back? Absolutely, there is. Stateful parsers called registers can help with this. And that's out of scope for now. That is something I can touch on in the second half, depending on what people want to see. So I just sort of want to talk a bit then about, what actually happens? What is Parsley up to? I've sort of mentioned that at compile time, I'm able to do this stuff. And that's why I had to get rid of these monads so that I knew everything that could happen up front at compile time. So I just sort of want to talk about, well, what does that mean? What is that compiler? And it's all based around what's called a deep embedding. So roughly, the operations in the parser are actually just constructors in some data type. The data type is ready for inspection and evaluation and things like that. But the point is, they are just data constructors. They just map to some abstract syntax tree. And the key thing is, once you have an abstract syntax tree, you can start to optimize it, you can start to analyze it. So something quite useful is with functors, applicatives, and selectives, they all have these laws. The laws are there to ensure that behavior is sensible. Now, sensible behavior often gives optimizations that sort of arise from it. Now, here are some laws that are in particular optimization directions. So the first one is sort of very obvious. If you have two pure things and you app them together, so you apply one to the other, you could just, because they're pure, just do that up front and return the result. So that's an optimization because we're no longer having to do three things. We have to do one. Associativity is kind of an optimization if you look at it from the right to the left, but actually it turns out to be a good optimization step to do other things if you go from left to right. And that basically says that you can sort of reassociate this app operation by using composition, function composition. Interchange is another one, and it just sort of says if you have an application on the right-hand side, you can always flip it around so it's on the left. And filter fusion says that filtering two things in a row means you can combine their predicates to get the same result. So these laws are sort of telling you something about how applicative structures relate to each other, and they end up being optimizations. And here's an example called applicative fusion, and it's sort of relying on these. So I'm not going to go too much detail into it. I'm just going to sort of show the steps and get to the end result. And now it's basically going to be using either definitions or those laws. So you sort of start by flattening out the structure, and immediately you can sort of see this associative application on the right-hand side. So you can just reassociate that and reassociate this again to get rid of the one on this side, and start to apply laws to sort of collapse a pure chain all together into one thing. Switching around this sort of application onto the other side and associating it again and collapsing another three pures suddenly leaves us with something that's a little bit smaller. So essentially, what this optimization has done is it's taken an F and a G applied on both sides and then putting the results together and just saying that, you can put these things together all in one go in one function. So essentially, whenever there's F maps and pures in a sort of linear stretch of parser, applicative fusion says that they can always just be put into one operation at the beginning. which I think is kind of cool. So that's sort of a taste of what sort of optimizations can happen in parsers. So, how do they get implemented? Well, in a deep embedding, when you have this AST, it's really easy. You can just pattern match on the tree and find the shapes for these laws that you were interested in. And that's, roughly speaking, all that needs to happen. So you go through, you pattern match on the cases you want, and you're sort of done. So it's quite easy to work with these in this form. And in a similar way, we can also do analysis on these things. But something, another interesting outcome from this, from the applicative fusion side of things, is that when we had this string combinator earlier, actually a lot of the work that happens during that combinator will get folded into one sort of application. So the idea of building the string as you go through the traversal will all get hoisted out into one value. So it's kind of nice to sort of shift all these things through. So analysis is something that we want to be able to do, and optimization is something we can do. And there's a need to handle recursion here, because you don't want to be optimizing infinitely for an infinite amount of time. And analysis as well, you often need to know where things come back on themselves. So as an example, if you have this parser here, this is the definition of the many combinator in many classical libraries. We'll see here that many p is referring back to itself. Now, for those of you who aren't quite aware of how Haskell works, this is truly an infinite computation. So, when you call many p, this will call the function many p. So, it will expand over and over and over and over and over and over again. It will get bigger and bigger and bigger as needed. Alternatively, you can express it like this with a let binding. Here, it's sort of using closures to sort of mean that p doesn't have to be passed by an argument. In this version, there's a sort of subtle difference. Go is a value here. It's not necessarily a function that's reevaluated. So go is referring back to itself. So this tree isn't an infinite abstract syntax tree. It's actually cyclic. So it goes back on itself. And the key idea is that Parsley can actually find this because they share the same, basically, address in memory. So it can sort of identify that there is recursion happening and it's right here. And the way this is sort of reflected is that we add this let node to the AST to sort of make clear where recursion happens. So you can sort of break recursive chains so that you don't optimize all the way down recursion forever and you don't analyze through recursion forever. So what analysis can I do? Well, I just want to sort of touch on a few interesting ones. And, I can talk more about them afterwards if that's what people want to hear about. So the four I've sort of picked out here, I think are really interesting ones. So cut analysis, leading character analysis, linear consumption analysis, and register liveness. So the first one is like, it's one that's sort of necessary to do a whole lot of other things. So here it's sort of identifying where in the grammar backtracking is and isn't possible, and sort of annotating that explicitly so you can find where things are sort of guaranteed to always happen together. Now that's useful for linear consumption analysis, for instance. So I'll get there when we've talked about leading character. So the idea of this one is, given some let bound parser, recursive or not, determine what its sort of characteristics are. So does it always consume input when it succeeds? Does it never consume input when it succeeds? And so on for failure. And more specifically, you can find out, well, what's the first character it would read if it were to succeed? So this is like in classical parser, field, it's the idea of the first set. So what is the first set of this parser? And actually trying to compute this subsumes termination analysis. So if a parser never consumes anything in its first set, or rather it's sort of the first thing it can do is get back to itself without having consumed input, it will loop forever. So you can actually identify, for the most part, when parsers do and don't terminate. And the sort of key intuition here is applicative parsers, always possible to know whether they halt or not. As soon as you introduce selectives and choice, it's not necessarily clear whether it halts or not, because we don't know under what circumstances different branches are taken. But sort of this analysis unlocks termination checking as well. And it's something I haven't quite implemented yet. I had termination analysis a while ago. There were a couple of broken cases, but I ended up removing it because leading character is just sort of a bit more useful for optimizing a few more things at a very low level. So linear consumption analysis is basically finding out when a bunch of characters have to be read all in one go. So for instance, if you're reading the string ABC, you know that you have to read all three of them at once. And if you can't backtrack out at any point, you can actually just factor out that length check and say, do I have three characters to begin with? If you don't, you might as well not look at whether they're A's and B's and C's. You can just leave. And register and liveness analysis is essentially where we have these stateful parsers, work out, do we already have them available? Do we really need to store them and collect them? Are they dead? Are they never used at all? In which case, do we need to have them in the generated code, or can we just throw them away? It's an interesting one for improving performance of like some niche applications. Or, context-sensitive grammars as well. So, okay, so we have this AST. Well, where do we go with it? The idea is it gets compiled to a stack machine. Now, stack machine, because context-free grammars, which is roughly what we're targeting here, are roughly push-down automata. So they're sort of a sensible abstraction, and they're quite a common one in the compiler world as well for implementing interpreters. They're quite lightweight. And so roughly you have a few stacks. One is for values that you're interested in, that you've been passing as you go. One is for dealing with failures as you're doing parsing, and the other one is the call stack. So when you do recursion, where do you go back to? This is sort of built into the language that you're building this on top of, so it doesn't really manifest directly. But this is similar to real stack machines like the JVM, like Python, other ones, and the instructions sort of implemented in what's called continuation parsing style. So here's a sort of example, and we're getting into the wonderful world of Parsley, where everything's got 100,000 type indices on top of it. So what on earth does this mean? Well, we'll call a machine M, and it has a few parameters. X is, so that's the values that are currently available on that stack, their types specifically. N is the number of times we're allowed to fail. R is what we produce when we return. So if we're in a recursive or a let-bound parser, what's our return value? And A is what end result we were trying to get out the parser. So parser A corresponds to an M something 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 A. So two basic instructions. Return says if you've got an X on the stack and we needed to return X, we're good. We can just return X. And push as well says if you've got an X, then if the next instruction along needs an X and some X's, then as long as you give me X's, I can put my X on the front and we can carry on working. So sort of concretize that a bit. If you have push 7 and then return, the overall type of this is a machine that expects nothing on the stack, and it needs to be able to fail exactly once. Now, that's just purely because this is a top level thing. So because it actually corresponds to something, the idea is we always can fail one time, and we return an integer, and it just so happens that's the same type that we're looking for, because this is the very final outward bit. So push 7 and return is the equivalent of compiling pure 7. You can get a bit more complex, so there's a few more instructions I can add on top. So pop does the opposite, says if the next instruction along doesn't care about X, I can just remove it from the stack. So give me X on X's, I'll get rid of X for you, it's all good. Lift 2 says if the next person along needs a Z, well, if you give me a Y and an X and then the rest of the stack, I can use this function X, Y to Z to combine X and Y and make a Z. Pop it on, we can carry on parsing. And so they're quite intuitive. There's more of them. They keep sort of unwinding as you go. So here's an example of this operation. It's called then. in Parser Combinator terms, you pass P, then you pass Q, and you only care about the result of Q because the arrow is pointing at it. And the way this works is we compile P, afterwards we pop its result, we don't care about P's result, then we compile Q and go and do something else. Similarly, if you want the other direction, you do P, then you do Q, then you pop and carry on doing whatever else you wanted to do. So they're quite intuitive how they translate across. And the nice thing is that the type indices that are so strong mean that you can't really get them wrong. The compiler just says, no, type error, if you've got the sort of wrong instructions in the wrong order. And there's another interesting one, case, which is used to implement these selective operations. So it says, give me two possible outcomes, one that wants an X and one that wants a Y. And then I just need either an X or a Y on the stack. So it inspects it. If it's an X, we take the first branch. If it's a Y, we take the second branch. So it's encoding that idea of choice into this machine. A sort of another interesting collection are things like alternatives. So empty is just the empty instruction. And the key thing about it is it's the first thing that ever says n doesn't have to just be n. It specifically says there can be n ways of failing, but there must be at least one of them because I'm going to need it because I fail. And the sort of way that ors and tries and other things are built up is a catch block. So this sort of tries, it's like try catch. It tries doing P and afterwards commit says, you know, I no longer care about failing. We can't deal with this anymore. And in this case, it sort of says, well, build a failure handler based on Q, which is the second branch. And if P fails before the commit, we can use this to fail. And it will increment this n as it does that scope. So what about recursion then? Well, recursion, have a couple of quite simple instructions and a lot of heavy duty machinery that comes alongside it. So two basic ones, call and jump. They are basically, you know, if you have a machine that returns that requires X, I can sort of jump to whoever can produce X's. We don't know who they are. They live in this map somewhere. And jump basically is like tail recursion optimization. It just says, you know, I don't need to do anything after I'm done. This would be what I do afterwards. So as long as the return types match up, I can just go there. So we have this machine, and this machine can be evaluated. How do you actually eliminate the overhead? So, you know, why do we have overhead here? Well, we have overhead because we have this deep embedding, this abstract syntax tree. And when you evaluate that at runtime, you have to pattern match on that tree. You have to recurse, you have to pattern match and recurse and pattern match. And that just takes a lot of time. And that's time that we just do not want to be spending, you know, at all. We want to just get to the point, which is parsing. So staging takes the center stage here. And I'm going to sort of briefly elaborate on what it is. So as a sort of example, this is how the state looks for evaluating these parsers. So it has an input, it has its operand stack, which is a heterogeneous list. And that's where the type X is sort of heads off to. The handlers, which is a vector of n handlers. So that's where the n heads off to. And a return continuation for, you know, when we're done. So give me my value R and the rest of the input, and I can go on to help make this maybe A that we're after as the sort of result. So given a machine of X is NRA, we give it a machine state of X is NRA, and we'll get back M may be A. So what does staging do? Well, at the moment, this can sort of be thought of as all runtime stuff. And in the staging world, we just call that code. So this point, by putting code in here, some of this stuff now runs at compile time, and anything inside code now runs at runtime. So this is sort of the identity operation. I haven't done anything here. At compile time, it just returns this function, and we're good. So we can sort of recognize that the structure of this parser, because it's all known at compile time, we haven't got bind, I can sort of push it in a little bit. So by squeezing the code to the right-hand side, this parser only exists at compile time. So now the deep embedding is just gone. It's already gone. And obviously, you know, there's There's a lot of other value level stuff to make that work, but generally this is the game we're playing. So deep embedding, all gone. Now we just have to deal with this function. And we can push it in again, right? We know statically what a machine state is. It's this for record. So why not just push it a little bit more and now move the code inside? So now when I call input and operands and handlers and const during my code, these all happen at compile time, and they provide me with runtime values as a result. So I can start putting them together in that way. So we've now gotten to a sort of function that takes 1, 2, 3, 4 arguments and returns a maybe A at this point. Now, some sort of interesting small fry is that when you have strong types means that you know something about the shape of this H list at compile time, right? We know how long it is. So we can sort of push that in. Now the heterogeneous list itself is a compile time thing, and these sort of values that used to be in it just sort of appear at runtime in the right places, right? We can just put them in the right slots. And in a very similar vein, of course, we know how big this vector is. It has a size n, that's in the types. So we can also squish that in. So this vector of handlers disappears, and handlers find their way to the right place in the generated code. So what's the outcome of all of this? Well, if we take something simple like this number parser, we pump it through all of this massive machinery, thousands of lines, and we get something that looks like this box. And I'm not at all going to explain what this is. I don't expect you to know, but it's sort of like, this is what ends up happening. This is what will get pumped out by the compiler. That's our end parser. And if you sort of squint at it a bit, it just looks like a handwritten recursive descent parser. And that's exactly what it is. So that's why I can get so close to that performance, because I'm really manipulating these combinators and code to generate recursive descent parsers. So that's sort of my overview of what's going on here. So what's sort of next? What do I want to work on next? Well, I'm in the middle of implementing optimized handlers. So, handlers can either say, well, input was consumed or it wasn't. Can you sort of eliminate that check based on how you know parsers perform? Yes. And part of that also involves termination checking and repair, because they follow very specific patterns. You can actually try and find those patterns and do the left factoring automatically. I want to implement inlining analysis because GHC sometimes does a poor job, and I can do a slightly better job with the extra knowledge that I have. So that's something I want to sort of work on a bit. As well, getting rid of register analysis and doing stuff like that is more work. And critically, error messages. And the fun thing about error messages is that a lot of the information about what makes up an error message is known at compile time. So a lot of that work to build them can be built at compile time, and they can just sort of appear in the generated code as these pre-built strings, which is a lot more similar to how a handwritten parser would generate these error messages. So that's sort of where I'm pushing. And I'm sure it will take me another couple of years to get there, but, it's all been worked on. So that's all I have basically for the first, for this sort of prepared segment. And I'm sort of happy to go in directions that anyone wants to see, essentially. So I can talk a bit about my more recent work about design patterns of parser combinators and how we can sort of encapsulate things. I know that a sort of a topic of conversation was about termination analysis and left recursion. And the patterns sort of address that in a more idiomatic way, but it can also show a conversation of how you can do it automatically. Or I could talk about registers if people want to know how stateful parsers come about and how you can sort of recover that original power. Or basically anything else. So I'm sort of open for suggestions about what people want for the remaining time, which I think is about 45 minutes-ish.
Yeah, thank you, Jamie. I'm interested mostly in left recursion and non-termination analysis, if it's possible. But you also said that the patterns solve the issue without actually needing to deal with that. So maybe it's
Yes.
better to.
Yeah, so I can sort of elaborate on that, I guess, a little bit. So I'll go over to my here's some I prepared earlier. Oops. So here we go, Teams as well. So yeah, okay. So the issue of left recursion. I'm going to just start by outlining what left recursion is and why it's a problem. So let's say I just want to read the most simple expression language in the world, right? Get rid of that for now. So yeah, let's say I have expressions and I want to read adds or numbers, really simple. So the BNF grammar for this would be something like this. So you'd have expras are either expras plus expra or a number, and then a number is, something else, right? Now, this grammar is kind of precedence agnostic. So perhaps a sort of better way is we can pick our precedents, right? Let's pick left associative. So in this world, numbers always have to come on the right-hand side, but you're allowed to keep expanding into expra again and again and again and again until eventually you just end up with a number. So, okay, I guess I can try and encode this and we can see what happens. So we can try reading an expra. In fact, I can even fiddle with this. Well, yeah, we'll fiddle with it. Actually, no, it doesn't matter. It doesn't matter. We'll keep it like that. So let's just try and read a number. And a number needs a num on the top of it. There we go. Or it's just a number, and I'll add the num construction around it. So what we've got here is something that corresponds to this grammar, right? So that's how it translates across. So, oh, no, I haven't done this right at all. Forgot to read pluses. That's a disaster waiting to happen. There we go. Oops, wrong direction. Care about that one. So you can see here, the type of this is parser expert. So this is the thing we're trying to seek out. Is it big enough for everyone, by the way, or do you want to make it slightly bigger?
It's okay for me.
Okay, that's fine. Make it ever so slightly bigger just in case. So the idea is, yeah, we're sort of modeling expra, there it is, the plus, there that is, and then the number, it's there, right? So we've encoded this thing, and it does compile, right? So it's all fine. So let's try and pass something. So let's print pass expra with 3. Just 3 will do for now. Show expra, yeah, cool. So let's see, does this work? And I'm really, it's stressful even doing this because I know what's going to happen. It's going to run forever. So the problem here is left recursion. The very first thing we do when we enter expra is we go and do expra, right? That's just not going to fly. So, if you're a classical parser person and you've been told that recursive descent doesn't deal with left recursion, what do? Well, you could left factor this, and that means a bunch of fiddling to change the shape of the grammar so that numbers appear on the left. And, trivially doing that means that you might accidentally right associate your tree, which isn't what you wanted in the first place. So this is a bit of a pain, right? But good news is there are some patterns. So in the Parser Combinator world, the sort of basic pattern for this is called chain L1. So I write out its type and then give a bit of discussion to it. Now, I have a more refined type than this, which is why I was playing around with making this an int. And I'll sort of demonstrate after I've sort of covered the basics of it. And now I'm going to set myself the task of remembering the definition of chain L1 off the top of my head, which isn't necessarily the easiest thing in the world. In fact, It's okay. It's okay. I know where I can find it. Whoop. Oh, wow. I'm good. Fine. Fine. We can mangle that. This is where you regret the fact that you over-engineer things. So it is roughly this. It's roughly that. Where? So here it is. So yeah, P on rest. It's an A. Rest is almost fine. Then I need this bit. There we go. Beautiful. It compiles. Okay, so what is this nonsense? So this is basically, it is the left factoring algorithm. That is what it is. So first we read the P's, and then we sort of say, okay, what's left? What's rest? And rest is here a function of type parser, is a parser of A to A. So it's sort of reading everything else. And the idea is it reads ops with P's on their right-hand side by flipping them over. So it sort of reads P, then an op with a P on the right, then an op with a P on the right, and an op with a P on the right until we run out. And it basically uses function composition to ensure that everything reassociates to the left. So this is actually the embodiment of the left factoring algorithm. This is what you would have done if you did it by hand. Okay, so how do you use it? Well, you'll say something roughly like this. So you'll say chain L1 of numbers with a plus and an add. And I need to patch up my numbers. And it could refer to either of them. Haskell sometimes. So yeah, this is how you end up using them. So this is sort of the idea, is the pattern takes away the left recursion and handling it for you, and you can sort of express, I want to combine numbers with additions, right? And it's a bit more of a concise way of building this. And this is a good example of the Combinator style, where we can build a tool for left factoring into our library without it having to be built into that language. Now, unfortunately, and I can run this, there you go. So we can pass threes now, that's good. Let's try 3 plus 4 plus 5, and hopefully we'll see that it left associates. So there you go. On the left, 3 plus 4, and then another 5. But, you know, I could make a typo. Oof. Oh, no. And now it's reassociated the wrong way around. So the sort of recent insight that I've had into this is that you can make this type a bit better. It's kind of useless because it gives you no indication of what the actual associativity is from here. And I mentioned earlier, I could sort of add the int on this side to sort of say, well, actually, this grammar says that numbers appear on the right and exprs appear on the left. And suddenly this doesn't work anymore because the types don't match up. So the way I've dealt with this more recently is making better functions. So by sort of making this B to A to B, you're saying that recursion happens on the B's. And I can magically make everything work all over again with a wrap there and a num there. So the cool thing now, the reason why this version's better is, and actually it's called, they're called infix R1 and infix L1. The point is, if I changed it to an R here, this no longer type checks. So it's sort of, you get this guarantee that the associativity is really what you wanted it to be. So that's sort of the canonical solution to this problem, and you can get a bit better. You can build precedence table combinators that sort of work a bit nicer for this. Is it a satisfying answer to the problem? From, you know, the most idealistic view, probably not, because you do have to remember to use chain L1, right? So So the reason I wanted to show the definition of chain L1 and illustrate that it was this sort of embodiment of the left factoring algorithm is that nothing about these combinators really isn't inspectable, right? We know all of their structures. We can recognize them all by seeing them. So there's a few different forms that these can take, but roughly speaking, at the deep level, at the AST level, I could pattern match for this entire structure. And so if I can identify, actually not this structure, we don't want to pattern match on this thing. I could pattern match on this thing, right? Or various other shapes of really left recursive grammars. They all follow very similar shapes to each other. It might be that, perhaps this is been taken away and put over here, perhaps, right? They're still, in essence, the same problematic parser, whatever. So you can pattern match on this and identify this structure. And in so doing, you can transform it into this shape by just substituting out for the combinator. So this process can be done automatically. It can be done automatically. So, you can see how all the components sort of fit together. The add moves over there, the num moves over there, and the numbers move over there, and expa moves over there, disappears, right? Recursion disappears. So, yeah, this is how we handle left recursion in the practical world. And in a world where you have that inspectability and you have the deep embedding, you could actually try and look for this shape and automatically do it. It's something that I want to work on once I've got that termination analysis in place. So once you've identified there is left recursion somewhere, you can then try and look and see if it can be patched. And if it can, sure, great, go do it. And then tell the user you did it, because really they shouldn't be writing left recursive things to begin with. Yeah, so hopefully that gives you a better sense of what sort of things can be done about this, and what the best way of normally dealing with it is.
Thank you. I like that you embodied the left associativity in the type signature, right? I haven't seen this yet.
No, this is something that it bugged me for a very long time, and it's such a simple change, right? With the addition of just this function to convert. It's a wonder no one has done it before. The fun thing about this actually is that in Haskell it's sort of clunky. You need this function. Most of the time, if you're thinking about object-oriented programming, right, where you have subtyping, really we're talking about the idea that that integers are expressions by subtyping, and this sort of num constructor can be a subtyping relation. So I have a version of this in Scala where actually this just disappears, and it's an upcast. So when your structure is recursive in subtyping, you sort of get this for free, which is really neat. It can kind of be mimicked in Haskell. You can implement a subtyping class and then add a subtyping constraint with A and B. You can write some template Haskell code to do that for you as well, which I've been doing recently. But it's kind of neat that in an OOP world, the structure is a bit better than in just plain Haskell. But yeah, having the type there makes so much difference to just ensuring that it works. The most extreme form of this as well, with the precedence tables, you can sort of use fixities to make this quite nice. So it looks like we've still got some time. So again, anything else anyone wants me to talk about, I am more than capable of doing. This is
one thing which has been bugging me since you've introduced the ManyP implementation via Go, where you then said that you can see the recursive structure in the AST, since it becomes a cyclical structure. But how do you deal with referential transparency in Haskell?
It's called a stable name.
Oh, okay, I see.
So
So you just cheat.
yeah, you cheat. So
Okay.
essentially, the way it works is the stable names are magic things that, as long as the value has been forced, will always be the same for the same value. So you just ask for them, and then you can compare them for equality, and you can hash them. So you can just build a hash map of stable names and find and hash sets and see, have I seen this thing before? Yes, I have. Okay, well, it must be recursive. And then you
Okay.
can go and patch that all up. Yeah, classic referential equality tricks. So that's why you need that sort of recursion by bound value, because that's the only way you can pick it up is when they have the same address.
Mhm.
But yeah, it's a dirty trick. More classically, people have sort of just used names. So you tag it with I don't know, something like that to sort of indicate at a combinator level that you've got recursion. I always hated that as a concept. And when I first implemented a library like this in Scala, it was so obvious. You just use referential equality. So I just did the legwork to figure out how to do it in Haskell as well.
Yeah, I think it's easier to make sure that compiler does this for you and not the user who you cannot even trust to
Yeah,
pick the names which are
absolutely.
different.
Yeah, when you have a string and that string can change, it is an absolute nightmare. Yeah. And it can take this a bit further as well. So the other nice side effect of this model is that if you do have something like, you've got P is A then A. Ugh, I'm not in Scala, I can't overload these things. And then you've got Q is like P then P. Well, good news is P has the same name on both of these sides. So you can actually translate that to a let binding in the generated code. So you don't, automatically inline and start to explode in size.
Mhm.
So it's just a neat trick that sort of allows you to mirror the structure on both ends of the universe. Because you could ask, well, how do you get parsers with arguments back? And then you have to start playing with the registers. So the
Mhm.
registers allow that sort of persistence. And then in an ideal world, they would just become arguments at the code level. Haven't got that far yet.
Yeah, it feels like it's time to just go to the registers now.
Yeah, okay, so registers. If you want to see
Uh,
registers,
I also
yep,
have some worries about staging. Do you have parameterized parsers when some parts of parsers are in one file and some are in another file? Can
right.
staging, I don't know, pull
Yeah,
information
yeah,
from one file to another, and everything works magically, yes?
yeah. So the way this works is if you define things across different compilation units, they are just going to inline in the generated code. So they don't like maintain any separation. At compile time, the code, the template Haskell AST from one and the template Haskell AST from the other file are just going to meet in the file that you're splicing them in, and they'll just come together. The good news is, of course, you never have to see the mess that happens underneath when the file just gets ridiculously big. But yeah, it sort of works to cross this boundary. Essentially, they all find their way to the splice file.
Okay, so template Haskell solves the problem and you don't worry about it.
Yeah, you don't have to worry about it. The only annoying thing is that in order to quote something, you have to make sure it's already defined in another file first, unless it's something from the prelude or whatever. Most of the time, that's not really an issue when practically writing these parsers. But yeah, this library here is not Parsley. If it were, there'd be a lot of template Haskell brackets all around the place. Not so many of them actually, but yeah, this bit would need to change. In fact, roughly speaking, the way this would shape out with some special plugins that I've designed for this, this would be how it would look in actual Parsley. There you go. So it's pretty similar, but yeah, the template Haskell will bleed in to your implementation, unfortunately. Get rid of that stuff. Yeah, okay, so I can talk about registers, unless there's anything anyone else wants to ask about. I will change language to do that. I will hop to Scala, because this library does not have registers implemented, and I'm not going to real Parsley. That's asking for trouble. Yeah, if not, I will just skip over to the other file, show you what I've got.
Is it a second or third version? I remember your initial Parsley Scala implementation was in Scala 2. I hope it is Scala 3.
Scala 3.1 doesn't exist yet. I was sort of waiting for Scala 3 to mature a little bit, because when I did it, I ran into a few bugs in the compiler. So I was like, cool, well, we'll give it a year to mature, and then I can port it over. But it has the meta programming in Scala 3 is very similar to Haskell's, so it sort of translates almost directly across, which is kind of cool. So I've switched to Scala and I'm using the original version of Parsley. This is the one from way back when in my master's thesis, which we now use at Imperial for the compilers course. A lot of people use it as their go-to library. So what I've got here, why is there a bunch of nonsense here? Well, to sort of illustrate registers, I want to show a very, very brutal and practical example. Now, here it is, magical thing. So this is, if you haven't worked it out already, the language that we'll call bran flakes, BF for short. And it consists of 8 operations that operate on some tape. And it is a very small example of a Turing complete language. Here's how you print hello world. It's this program here. There it is. I'm not going to go and explain what it does. And if you wanted to echo, you can use this program here to echo something out. So the actual, parsing in this language is really, really, really easy. So I'm going to define this. This is Scala 3, by the way. I'm going to define this enum that represents each of the operations in the language. Pretty straightforward. And here's the parser that just does it, right? So it's quite straightforward. It is read some white space, then some operators. Here they are, get a list of ops back. That is 0 or more ops. And that's either you read a right character, that's called the right pointer operation, left character, left pointer, and so on, right? And then between square brackets, you have some more operations and they form a loop. So this is a parser that implements this language. Now, what I want to express is when you lose monads, you lose context sensitivity. And my claim is that when you take selectives and you add registers on top, and we'll see exactly what registers are, you get back Turing power. Now, what's the best way of showing Turing power? Implementing a Turing complete language. So we have a parser for brown flakes. Cool. But what if we had an evaluator for brown flakes built into the parser? So this is what I'm going to sort of implement here pretty quickly. And I can sort of show, well, what are registers, how do they use, and why does it get so awful? So the idea is basically we prepare, we pass the input, and then immediately we'll get the result back. That's essentially the idea. So prepare is actually going to return a list of ints, and that ints is the things that were outputted. So that's the dot operations. In this case, I've turned them all into characters, strings, so that we can actually see hello world pop out, for instance, and we can actually add some input and echo stuff, like echo looks like echoing works, should print out looks like echoing works. So let's begin. Let's find out what on earth I'm going to do to make this work. So it turns out I need 3 registers. to make this all work. And it starts to become evident how this sort of model of parsing ends up doing stuff. So I need a register that stores the list of operations I need to execute, my tape, which is the scratch space that all the values will work on for the language, and I need somewhere to store the output as it's going along, this list of integers. So these sort of abstractly represent locations where this stuff will be stored. And I'm going to start by plopping just a little bunch of stuff in here just to discuss it just ahead of time. So there we go, get that out of the way. So basically, how does this parser operate? Well, the first thing we'll do is we'll just parse BF. So that's this parser here. So we'll read all of the operators, and as we remember, that gives us a list of operators, and we'll put that into the instructions register. So in they go, they live in there now. We can get them out when we need to. The point is they've gone into this state. I'm using this $ as a delimiting character between the brown flakes program and the input that that program requires. So the actual parser first loads in the program and then passes any input to that program, which is the fun bit. As for the tape, we'll pop the empty tape. This is just the class I've used to represent an infinite tape on both sides, and we'll put the empty list in the output. The idea is then we go and evaluate, whatever that means, and afterwards we should be able to get out of the out register our final results, reverse them to flip them all around the right way, and return those. So how on earth does this look? So this is probably going to look horrific, and it really is. But what you hopefully will start to see is it kind of looks a little bit like I'm imperative programming, and that's because I really am. So I've got this combinator called predicate. It's essentially an if statement. So read something on this side, in this case, get the instructions. So that's the list of operations. If they're empty, then we're done, return. Otherwise, if it's not empty, then go get the first one, right? And persist it. So this is using a register basically to allow us to access this operator more than once. In fact, I want braces for this. There we go. So, so what does that mean? It means we can sort of collect the value of op over and over and over again without reparsing it. Essentially, this is bind, but the restriction is you're not allowed the op itself. You're allowed the parser that gives you the op. So it's sort of still static structure in a sense. So a bunch of stuff is now going to happen in here, and that's going to actually be the implementation of this parser. So we've got to figure out what goes here. So what's going to happen in here first is first thing we're going to do is throw away the head thing. We've already got it. It's called op, right? We can look at that whenever we want to. So we can sort of throw it away at this point. And then we'll go and evaluate op. We don't know what that is yet. And once we've evaluated that one op, we'll just go and eval. So we'll go back, recurse, and do more things. Cool. So question is, what goes in this blob? So we have eval op. Doesn't have a result. So the key thing about this is kind of like probably noticing at this point, none of these things have any results. They just return unit. Hallmark of imperative programming right there, right? The results that we want are kept in these registers, so we can get at those when we want to. We don't need to return them in the parser. So what is going to go and happen in here? Well, meet the selective answer to bind, which is a horrific combinator, by the way, but we're going to use it regardless. So this combinator basically takes so it takes a set of values that are possible. So in this case, we're saying that the result of op can be one of these things: right pointer, left pointer, increment, decrement, output, input. Notice loop's absent. Loop's the default case. So if it's none of those, it's going to be a loop. We'll go and eval loop whatever that means. So this basically gives us the ability to inspect them, right? So we can actually case them on each thing. So the sort of magic here is this seems a bit like a bind. It's not a bind because there's finitely many things it could be. So we can just walk through them one at a time and say, is it this one? No. Is it the other one? No. And so on. So the implementation of this, if you had an infinite set here, would take you an infinite amount of time to traverse through and find out what everything does. So not ideal. So, what do we do here? Well, if the operator is a right pointer, we should modify what's in the tape register by shifting it to the right. And equally, here, we want to modify the tape and shift it to the left, right? So I'm just going to copy all of these things because they're relatively samey, and just say, well, what has happened here? So we've got, in the increment case, modify the tape by adding 1 to the center cell, or subtract 1 from the center cell. Output gets the output of the tape. It reads the head of the tape and adds it to the out register. So remember, this is where all the printed output is going. So, this is roughly read tape and then write it into out, right? It's very imperative. Do this, then do that, then do this. Input's an interesting one. This is called item, as I've currently called it. It's called NHR for whatever reason in Scala Parsley. So we modify the tape register, and what we should do is read any character at all. And what we'll do is we'll just modify the tape by writing that character into the first slot. So this is how the input gets read. In fact, it's the only part of this parser, and I put parser in quotes, that actually does any reading. Everything else is entirely mechanized states. And this case is just to make the compiler happy. It really can't happen. So that's the loops. So what happens in loops? Well, lazy val loop, val loop, rather. Again, we can guess what its type is. This is an imperative program. So unit. So what happens here? Well, the way that brown-faced loops work is that you check whether the current location on the tape is equal to 0, right? If it's equal to 0, then the answer is unit, right? The loop stops running. Otherwise, what do we do? Well, for a while, that's what local means. Body. So take the operator and extract the body. Make that the new thing in local, in instras. So now the instras is full of whatever is in the body of the loop for a while. What do we mean by while? Well, during eval. So for the duration of this parser, the op's going to contain the body of the loop. Afterwards, it's going to go back to whatever it was before. And that requires another register. So there's another register who comes along to store the old thing and puts it back again. So, we've got registers oozing out of everything here. Then what do we do once we've evaluated the loop body? Well, we go and evaluate the loop again because we've got to check if it's 0 yet. And that is that. That's the entire interpreter for this language. And yeah, it's basically, if you were an imperative programmer and you wanted to implement this language, it's exactly what you'd be going and implementing in your language. So does it work? Well, let's see. Let's run it. And hopefully, as long as I've not screwed anything up, there you go. Hello world was printed by reading the first program, and turns out echoing also works. So there you go. I echoed hi, I got hi back, and it looks like echoing does in fact work. So what does that tell us? Well, it tells us that not only can I just make ridiculous parsers in my spare time, but it shows us that, yes, registers and selectives, which is everything we've seen here, is sufficient to implement a Turing-complete language. So that's a register operation. Anything involving all of these little things is registers. and predicate and match are selective operations. And if you're curious about how map is implemented, in plain selectives, it's a total, not a mess. If you get access to registers, you can sort of make it a bit nicer by folding through that set and using an if statement on each thing in turn. So that's that. There you go. That is registers. And they're crazy little beings, but they are useful for all context-sensitive things. So I think the cutest example is the for combinator, where you can treat it like a for loop. So if you want to read the classic language, which is like matching A's with matching B's and matching C's, all n of them, you can use a for loop. So you read A's, count how many read, and then for I down to 0, read B's. For I down to 0, read C's. It's a very concise way of reading these things. But other than that, yeah, registers are a total mess for dealing with on a regular basis. But I find them fun. So yeah, any questions about that? It's probably quite intense, but this is how it goes with registers.
It feels like registers and selectives are enough for everything in parsing, right?
Yeah, they're enough for everything. It's just it's your definition of everything kind of varies. So I said earlier you couldn't implement join. You can implement join if you have the two of them. Obviously, it's Turing complete. No one said that's easy. So in order to implement that, in order to implement join, and for people that don't know, the signature of join is like this. So we can roughly think of this a bit like a join, where first you sort of read the program to make the parser. So an example of this is like reading a regular expression delimited by $. So you say AB star, and then you give it some input. So the one of the ways to implement this is first read AB star and turn that into Parser Combinators, then join it to allow it to read the input afterwards. Can you do this? Yes. Is it easy? No. In order to implement this, you'd have to implement an interpreter in this style here for a Parser Combinator library, in a Parser Combinator library. So yes, it's possible. Would I ever be crazy enough to do it? No. So yeah, it's like they're powerful enough to do everything. It just depends on how much willpower you have to actually go and do something like that. But yeah, it's kind of interesting. Most of the practical workloads that you'd want to do, these are sort of straightforward. For the over-engineered workloads, they start to become a bit obtuse. But that's the trade-off that you've got to make.
Maybe we could find any idea to take monadic parser combinators and maybe rewrite them to something more, I don't know, automatically, I mean, to more selective, I don't know, to have more speed or something.
Yeah, I'm not sure how to do that. The tricky bit is inspecting the function. So using staging, you can't do that. You can't peek in the function. So you can, but it's ridiculous. It's sort of the realm of a compiler plugin. So maybe compiler plugins could do this, similarly to how they made applicative do. Originally, it wasn't a compiler extension, it was a plugin. So you could do something like that. I mean, technically, you could try and make one that uses registers to do it.
What is the difference between plugin and extension?
Well, really, the difference is that one is built into the compiler and one isn't. But plugins are sort of limited in their power. Extensions can exist anywhere in the compiler, right? So a plugin can only hook into the bits the compiler has exposed for them. Extension developers can just extend them. They just get to write a bunch of code inside GHC, so they can do anything. That's roughly the difference. So in theory, you could do it. I'm not sure how much benefit you get. I think it's quite difficult to find selectives in the wild. they sort of follow these very specific patterns. So I'm not sure to what extent you could generalize it, but certainly it's something that someone could explore. A compiler plugin would be the way.
Somebody probably should do it because using selective is not very fancy.
Yeah, using selectives can be really painful. I mean, some of them are quite nice. So filter, I quite like because it is quite easy to use, and it does manifest in Scala Parsley as .filter, which actually means if you use for comprehension style, you can actually write it something like.
Have a great evening.
Thank you. You can actually write something like, if x less than 10 or whatever, and that does compile to filter. But yeah, stuff like predicate is where it starts to get clunky, and you always know you can replace your if statements with predicate, but it's like, a little bit of pain to do that. So I guess, yeah, like, can you recognize an if statement in a do block, turn it into selectives? Probably, yes. Can you find filters? Probably, yes. Can you find a program like this? No. Probably not. I think that would be asking a bit much of anyone. But yeah, it'd be an interesting avenue to explore, I think. Anything else? Anyone got any other questions? I guess not. I guess we've satisfied everyone's curiosity for the day.
Yeah, we're very glad to see you today and to hear. It was very interesting.
Yeah, no problem. Thanks for having me.
Thank you. I really enjoyed the talk.
Thanks. It's always fun when I'm actually in my element when I have 0 things prepared. I live code all my lectures. So yeah, getting to finally do a recorded talk where I actually pull out a VS Code window is quite fun. But yeah, I have actually implemented this parser before, although I did it live in another talk. That was interesting.
I also got a feeling that you prepared some code and copy pasted it to your screen.
I did. Yeah.
It was not very obvious how did you implemented it, because I was watching on the mouse and this mouse wasn't moving to another window or something. It looks like you have prepared some hotkeys which pass the right code in the right places or something.
No, they're just here. There they are. The magic of having more than one monitor is that it's really easy to pick up this stuff and collect it. But yeah, no, I did this all live in another talk, so I had it all prepared. I wasn't going to do that again, because I kept making it loop forever last time. But yeah. So again, yeah, thanks for having me, and I hope that I've answered all of your curiosities that you've had probably for so long now, and yeah, thanks again.
Thank you.
Many thanks.
I can get